say something about the P-wave quantum annealers.
Hello, and thank you for coming. First thing I should say is what I'm going to talk about is, in a sense, sort of an advanced topic. Crystal gave an excellent introduction to the basics of our system. I'm going to sort of assume that you understand all of that, and I'm going to talk about some advanced features which we've introduced just recently. So this chart is actually intended to capture progress over the past few years, since about 2011. The chart shows our first system that we introduced in 2011, the D-Wave 1, and if you look at the third column over, you'll see the qubit count. That was a 128 qubit system. I should point out that before 2011, we actually had a sequence of prototypes in our lab that were much smaller. You know, we started with 4 and 12 and 28 qubit systems. But the first system that we actually introduced commercially was the D-Wave 1, and that was 128 qubits. A couple of years later, we went up to the D-Wave 2, which was 512 qubits. 2 years ago, we introduced the D-Wave 2X, that was 1152 qubits, and then at the beginning of this year, we introduced the D-Wave 2000Q, which has 2048 qubits. And I give some formulas here that actually allow you to compute the exact number of qubits in our system as a function of the so-called geometry parameters. The geometry parameters just tell you the size of a square grid of these unit cells, and each unit cell has 8 qubits in it. So this is what we call our chimera topology, and the fact that we've been able to introduce more qubits and more couplers with each generation has been very exciting for us because it's allowed people to map larger problems onto the system. But what I really want to talk about for the next few minutes is some features that actually we've introduced with the latest generation system that allow the user to have more precise control over this annealing cycle that Crystal described. So this is the time-dependent Hamiltonian that describes the evolution of our system as it goes through the annealing cycle. And the first term, the A of S multiplied by the summation of these sigma X matrices, that represents the quantum fluctuations that allow the system to tunnel from state to state. The second term that's multiplying B of S is the energy landscape. And that energy landscape is controlled by the programmer. The programmer controls the parameters A and B that determine the individual biases on the qubits and the strengths of the couplers. And the graph that you see at the bottom represents these two curves, the A and the B curve. The A curve represents the strength of the quantum fluctuations at a point in time, and the B curve represents the strength of the energy landscape at a point in time. And that's as we go through our annealing cycle, which has a duration typically of around 20 microseconds. And as Crystal pointed out, the reason we architect our system this way is so that the optimization problem that you see on the bottom of the slide can be solved by using this adiabatic process. So this is the fundamental working model of the system. But what I want to introduce is some features, advanced new features in our annealing control that we've introduced and are continuing to introduce over the course of this year. And I'll roughly call them anneal offset, anneal pause, and anneal quench. So what these mean, I'll take them one at a time. Anneal offset means that rather than each qubit following this trajectory that you see here, That means that we can actually individually and independently retard or advance individual qubits as they progress through this annealing cycle. And there actually are very good reasons for wanting to do that. Our initial motivation for providing this additional level of control was to allow us to more precisely calibrate the system so that this physical device actually behaved more closely to the idealized model that we've written down here. But in addition to calibration, it turns out that this provides the users some power to actually improve the performance of the machine. And I'll show an example of that in just a couple of minutes. The second and third features I'll call anneal pause and anneal quench, or sometimes ramp. And the idea behind these features is that midway through this annealing process, we can actually freeze the annealing parameters, the A and the B curves, and we can allow the system to stay fixed in a particular, with a particular mixture of the quantum fluctuation terms, the sigma x, and the energy landscape terms, the sigma z terms. And so at that fixed portion in this pause region, the system is actually behaving as a full quantum mechanical system because we have both sigma x and sigma z terms present driving the dynamics of the system. I'll show a second example that demonstrates the use of that feature. So to talk about first the annealing offsets, I'm trying to move a little bit closer to something pragmatic here. This is a sample problem which is factoring, integer factoring. If you have familiarity with quantum computing, you know that one of the big drivers of interest in the field from the early 90s was Peter Shor's algorithm for factoring integers on a circuit model or gate model quantum computer. Now, we build a quantum annealer, not a gate model system. What that means is that Shor's algorithm does not run as it stands on our machine. But it is still possible to factor numbers on our machine, you just do it a different way. So this is work that was actually done in late 2016 by a team of half a dozen people at our company headquarters. Bill McCready, Aidan Roy, Andrew King, Marshall Drewbrook, Fabian Chudak, Jingban Bian, and Evgeny Andriash. So the way you do factoring on our system is actually pretty simple to describe. In this example, we're taking two 4-bit binary integers, we're multiplying them in exactly the same way that you would be taught to multiply by writing out the products of the individual digits and then summing down the columns. So the product of these two 4-bit binary integers gives you an 8-bit number. And then what we do to program this on our system is we effectively take this logic circuit and we embed it into the fabric of qubits on our system. So here's an example of what that looks like. This is actually using a 5x6 array of unit cells in our system. So that's 30 unit cells, 8 qubits per unit cell. So this is using a total of 240 qubits in order to do this factoring problem. To a unit cell, and then we connect up the unit cells to create the entire multiplication circuit. And then the interesting thing about how we perform factoring is now that we have this multiplication circuit embedded in our chip, any ground state of this problem will be a valid multiplication. So in other words, if I'm multiplying two 4-bit integers to get an 8-bit integer, that would mean that, 7 times 6 equals 42 is a valid ground state. 3 times 5 equals 15 is a valid ground state. All possible multiplies are equal energy, valid degenerate ground states of the Hamiltonian that we craft. So now what we do is we take the output bits and we bias them. So if I'm interested in factoring the number 15, I would bias the 8 output bits to represent, the binary representation of 15, and then out of all the possible ground states, now the ones that remain degenerate and at the bottom of my energy well represent the factors of 15. So, colloquially what we say is we run the factoring circuit backwards to get the answers. When we do this without using anneal offsets, one thing that we discover is that as we try to factor larger and larger numbers, our ability to hit the ground state reduces. So in this graph here, you'll see I'm showing in the blue bar problem sizes of 6, 8, and 10 bits. And you'll see as we go from 6 to 8 to 10, the number of, or the success rate, as measured by the height of that bar, the success rate is dropping. So at 6 bits, I'm reliably able to factor every time. At 8 bits, my factoring rate drops to around 50 or 60%. And when I get to 10 bits, I'm well under 10%. So that means I would have to pull hundreds of samples from my system in order to be guaranteed of getting a valid answer. But using the anneal offset feature, we can actually tune the trajectory of individual qubits as they move through the annealing cycle. And you can see in the maroon bar here, there is much less degradation in performance as I go from 6 to 8 to 10 bits. So in fact, when I'm at the 10-bit range, I'm reliably able to factor at about the 90% level. So I'm not saying that this trick of using anneal offsets is generally applicable to all problems, but this is sort of I'll call it a proof by example. There are at least certain categories of problems whose performance seems to dramatically improve through the use of some of these advanced annealing features. We haven't really explored a wide range of problems, so it's very hard for me to, say this annealing offset technique will work for, this class. qubits. And these chains are strongly coupled to one another so that a chain of 4 physical qubits behaves like a single logical qubit in the 3-dimensional Ising model. I won't go into details here, but what this picture illustrates is a pair of unit cells on top and a pair of unit cells on the bottom. So this is 4 unit cells. You can see it on the left side of the picture. Each one of those unit cells has 8 qubits in it. So 8 qubits per unit cell times 4 unit cells. We have 32 physical qubits here. The picture on the right side shows you how Richard has grouped together those 32 physical qubits into 8 groups of 4. You'll see there's a horizontal red line and another vertical red line. Together, that represents a set of 4 physical qubits that are strongly coupled together, and so they will behave as a single logical qubit in the 3-dimensional lattice. If you look at the other colors here, there's a dark blue, an aqua, a green, kind of a brown color, another blue, sort of another green, and another green color. So together, what you're seeing in these colors represents 8 logical qubits in the vertical dimension of the 3-dimensional lattice. Now this is a set of 4 unit cells. Our chip is a total of 16 by 16 unit cells. So this is the vertical dimension, and then the other dimensions of our chip give you the 2 horizontal dimensions. So in essence, that's how he mapped a 3-dimensional cubic lattice into this 2-dimensional structure. And then the experimental annealing parameters that Richard worked with, you can see here explicitly that in the middle of the annealing cycle, he's holding the system fixed. Normally our annealing cycle has a default duration of 20 microseconds, but what Richard did is to hold the system at an intermediate point during the middle of the anneal for 1 millisecond. That's 50 times longer than we would normally be at that point. And so during that 1 millisecond interval, our system is behaving as a 3-dimensional nearest neighbor coupled Ising model with a transverse magnetic field. So it is a quantum system during that part of the anneal. And what Richard was able to see very clearly, this is in effect the simplest result that he came up with, but this diagram represents on the left the paramagnetic phase, and then on the right you can see that the order parameter, which represents the magnetization of the spins in the lattice, is turning on. So he was able to see a very clear signal for the phase transition that we expect in a 3-dimensional Ising model with a transverse magnetic field. And then the last feature that I'll mention very quickly is what I'm going to call reverse annealing. We haven't actually released this in our software, but the idea is that we can actually allow the user to pre-initialize the values of all our qubits and then go through our annealing cycle in a reverse direction, which looks like it holds some very, very interesting algorithmic potentials for maybe doing quantum parallel tempering as we try to do a better job of looking for ground states in these complicated energy landscapes. So to finish up, I'm sorry if this has been sort of too technical, but the point that I want to get across is at the same time that we as a company, D-Wave, at the same time that we're trying to increase the number of qubits and the number of couplers in our system, we're also trying to increase the kind of controls that the user has over the annealing process that our system goes through. And the hope is that by improving the control that the user has over the anneal, then we'll be able to increase the system's ability to hit ground states and also actually simulate genuine full quantum systems.
Okay, Danny, thank you for your presentations.